Hello and welcome to my Maths Week 1 Video 4. In this video, we'll be covering the second part of the topic which we had started in our previous video, which was series. So in this video, we'll be going into a lot more detail, specifically with geometric series. So let's start off with a concept that is probably new to you, and one that isn't often spoken about in your mathematics curriculum. That is the concept of limits. Okay, so what is a limit? A limit is simply the value that a function approaches as let me just fix my grammar there. No apostrophe. As its input approaches a given number. Okay, so what does this mean exactly? What does it mean? Basically, you might be a bit worried because you're seeing something related to functions and we're in sequences now, so that might seem like we're mixing things up a bit. But in maths, everything is interconnected. So you will have to get used to the idea that you do need to borrow knowledge from some other areas and some other topics to make you fully understand a certain concept. Okay, so with limits, basically a limit can be written like this. This is notation for a limit. When we say the limit of f of x as x approaches some number a, we read it as the limit as f of x, or the limit of f of x as x approaches a. Basically what this means is, what is f? What is our function f approaching as x approaches a certain number? Let me give you an example. Let's say that f of x was equal to, let me use a different number here. Let's say it was equal to 5x, okay? So what does the graph of f look like? Let's just plot it out. The graph of f would look something like this. It's a straight line passing through the origin with a gradient of 5. Okay, so that would be f. Let's say that we wanted the limit of f. I can write 5 now, 5x I mean. The limit of f as x approaches, let's say 2. What is this equal to? What does it mean, first of all? Basically, it's saying, what does 5x approach as x approaches 2? We know that when x is 2, 5x is equal to 2 times 5, which is just 10. Okay? So you're just plugging it into the formula here for f of x. So we can see that as x approaches 2, as x gets closer and closer to 2, our f of x, or our y, gets closer and closer to 10. So that simply means that the limit is equal to 10. That's all it means. Simple as that. So this limit is equal to 10. Okay? So let's look at something that's a bit more abstract. Let's say that we wanted the limit of f of x. We're still going to use the same f of x. Let me just write it as 5x as x approaches infinity. Okay, what does this mean now? All right, so let's refer back to our diagram here. Let's just remove a couple of these. Right, just clean this up. So go back to purple. Basically what they're saying is, as x goes to infinity, what does 5x approach? Okay, so we can see that as x goes further and further and further and further out, approaching infinity, what will happen to f of x? This line keeps going up, right? Keeps going up and up and up and up. So what is f of x approaching, since that line is continuing to go up? F of x is also approaching infinity, because it's getting bigger and bigger and bigger and bigger. It's not slowing down, it's not going backwards and becoming smaller again. As x gets bigger, 5x or f of x gets bigger. So we would say that this limit is equal to infinity, because as x is going to infinity, 5x also goes to infinity. All right, so let's look at a couple of more examples. Call this, okay, let me just write examples. Okay, so soon you'll see how all of this links up with series. Okay, so let's look at another example. Let's say that we had f of x is equal to x squared. Then we wanted the limit as x approaches, let's say 4 of f of x. So what does this mean again? Let's draw out our graph. Looks something like this. I hope my lines are straight. No, they aren't. That one doesn't look anywhere close to being straight. Okay, that's a bit better. Let's use red. So rough sketch of our graph looks something like that. Okay, so that's f of x. I'll just write f. So basically this limit is asking us, what does f of x approach as x approaches 4? Okay, so let me just use a different color here. When x is equal to 4, what is f of x equal to? It's just equal to 4 squared, which is 16. Okay, so now we can answer this question. As x gets closer to 4, as x gets closer and closer to 4, y is getting closer and closer to 16. Remember that y is f of x. They are the same thing. So as x goes to 4, y goes to 16. So this limit will be equal to 16. Okay? So let's say that we had a different limit now. Let's look at the limit to infinity again. If we had the limit of f of x as x goes to infinity, this should be simple now, because we can see that, oh, let me just erase that part. Okay, so we can see that as x becomes bigger and bigger, this graph keeps going up like that, in that direction. So it should be simple for us to see that as x goes to infinity, y should also go to infinity. So we can conclude that this limit is equal to infinity. Okay, so we can see how limits sort of work now. Let's look at a slightly different example. Let's say that we had something like this. F of x equal to 2 to the power x. Okay, so I want us to evaluate this, but without drawing out the graph. So how would we go about doing that? The way we would do that is look at the behavior of this function as x gets bigger and bigger. Does it keep on getting bigger, or does it slow down at some point? That will tell us whether the limit is infinity or it's some other value. Okay, so what does that mean exactly? What does all of that mean? Think of it this way. As x gets bigger and bigger and bigger, approaches infinity. Oh, let me just write out the limit that we want to find first of all. That's the limit that we want to find, okay? So as x gets bigger and bigger and bigger, as it approaches infinity, we're substituting a bigger and bigger number here, right? So what happens when you substitute a bigger number into the exponent? You get a bigger answer, right? So we know that bigger number in the exponent gives us a bigger answer or a bigger value. So we can imagine that as this exponent approaches huge numbers like 1,000, a million, a trillion, we will get a very huge value here as our answer. F of x will get very big. Remember that our exponent here is basically x, and our value here is f of x, 2 to the power x. So as our exponent x gets bigger and bigger, our function value here, our f of x, will become quite enormous. So we can see that f of x must be approaching infinity as well as x is approaching infinity. So without having to actually draw out the graph, we can see that this limit is equal to infinity. If we want to confirm, we can draw out our function and see what it actually looks like. So just to make sure that we actually correct, we can draw out the graph. It's an exponential function. Looks like that. It cuts the y-axis at 1. So we can confirm by saying, okay, what does y approach as x gets bigger and bigger and approaches infinity? Y also gets bigger and bigger, right? It goes up. The graph keeps going up in that direction. It's getting much bigger and bigger for each value of x as it's increasing. So we can see that from the graph, this function does approach infinity as x approaches infinity. Okay? So we can confirm limit, it is infinity. Alright, so we can see that it is possible for you to find a limit without actually drawing out the graph and doing all of that. Just look at the behavior of the function. Alright, so let's look at our next example. Let's say that f of x was equal to 1 over 2 to the power x. And we want to evaluate the limit as x approaches infinity of f of x. Okay? So we want to do this without drawing out the graph. We can draw the graph afterwards to confirm our answer. Okay? So how does this behave? What does it look like as x gets bigger? Okay, we know that as x gets bigger and bigger, this function will either get bigger, it'll get smaller, it might remain the same, who knows? We'll see as we analyze this problem. So we know that from the laws of exponents, if you have a fraction raised to a power, let me write it out here. If you have a over b to the power n, that's equal to a to the power n divided by b to the power n. So the law of exponents tells us that you can distribute this exponent between the numerator and the denominator, right? So if we simplify our function here, we get 1 to the power x divided by 2 to the power x. We know that 1 to the power of anything is just 1, right? Then 2 to the power x remains as it is. So let's rewrite our limit down here. We know what f of x is. it's 1 over 2 to the power x. I'm just writing it in this simpler form. Okay, so what happens now to the value of f of x? What happens to f of x, our function here, as x gets bigger and bigger, as x approaches infinity? Think of it this way. We know that a fraction like 1 over 81 is smaller than a fraction like 1 over 3, right? We know that 1 over 1000 is less than 1 over 2. We know that 1 over 333 is less than some fraction 1 over 5, for example. And what is the reason for this? The reason is, if your numerator is the same, as you divide by a bigger and bigger number, your fraction gets smaller. Okay? So think of it this way. It's like taking out, let's say that we have a block here that has a length of 1 meter. If you divide it into two lengths, each length will still be pretty long, right? It'll be 0.5 meters. But if you were to take the same block and divide it into 1,000 pieces, we obviously won't be able to draw 1,000 pieces here, but you get the point. If we were to divide it into 1,000 pieces, each piece would be very, 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 very small. So that shows you that as you divide by a bigger and bigger number, your fraction gets smaller. So let's try and apply this here. We can see that if we had, let's say, 1 over 2 to the power 10, then 1 over 2 to the power 100, 1 over 2 to the power 1000, all of these fractions are getting smaller and smaller as x is increasing, right? So we know that we're dividing by a bigger number, right? So our fraction is getting smaller and smaller. Okay? So what does this mean exactly? What does this mean for our function? What is this function going to approach as x gets bigger and bigger? We can see that it's getting smaller, right? So it must be approaching 0. Okay? So our limit here should be equal to 0. Okay, so I hope that you do have some type of grasp of that, because as x gets bigger, let me just highlight this, as x gets bigger, our denominator, the bottom of the fraction, just explodes, becomes huge. But what's going on to the entire fraction? The entire fraction is becoming smaller. Okay? So we can see that since x is going to infinity and this entire fraction is becoming smaller and smaller, it must be approaching 0. Okay? So let's just try and solidify that idea with the graph. Let's draw our graph of the function f of x. What does it look like? Okay? You can confirm this. The function looks like this. Cuts the y-axis at 1. It's an exponential function. And what do we see? As x gets bigger and bigger and bigger, as it's approaching infinity, y is getting smaller. The function keeps going down that way. Keeps going down, 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 closer and closer to 0. Okay? So f of x is approaching 0 as x approaches infinity. Alright, so that's basically the basic idea of a limit. That's the basic idea of a limit. And this might or it will be very useful to you in terms of understanding series. So let's actually move on to actual series. so we can see where this applies. Series. Okay, so let's do this. Change to white. Think of this. In this unit, or in this topic, we're covering geometric series, right? But why aren't we doing arithmetic series? Why aren't we doing quadratic series or series like that? And what you'll realize, this comes to the issue of convergence and divergence, which we will cover in this video. What you'll realize is that with arithmetic and quadratic series, there's no point in calculating them because they all approach infinity or negative infinity. Okay? So let's actually see why we're saying that. Let's say that we had an arithmetic series. And now, instead of talking about summing up the first n terms or summing up the first 10 terms or 100 terms or whatsoever, we want to talk on a much bigger scale. We want to talk about the sum to infinity. The sum of an infinite number of terms. So you'll see that now our knowledge about limits might come in handy because we're starting to talk about infinity now. Okay? So let's say that we had an arithmetic series that looks like this. It's, say, 2 plus 4 plus 6. It's a series, remember? So we're adding. Plus 8 plus 10 plus 12 plus 14 and so on. Let's say that we wanted to find the sum to infinity of this series. And what does the sum to infinity mean? It simply means that you're adding up an infinite number of these terms. Okay? So for an arithmetic series like this, what do you think the sum to infinity will be equal to? Okay? What you'll notice is that each term is bigger than the previous one, right? Each term is bigger than the term before it. So as you're adding them up, your sum to infinity gets bigger and bigger and bigger. It's not getting smaller at any point, or it's not slowing down, right? So what should this tell you? It should tell you that as n approaches infinity, the sum of the first n terms should be equal to infinity. Okay? I hope that makes sense. So let's actually try and dissect that statement. So we see that first we have a 2, then a 4, then a 6, and 8, and 10, 12, 14. These numbers are getting bigger and bigger. So as we add them up, their sum should be getting bigger and bigger too. So we can expect that as n gets huge, the sum will also be huge. So our sum to infinity will be equal to infinity. Okay? Let's actually try and prove this in some way. Let's say that for this series, let's write out what Sn is equal to. Sn is n over 2 into 2 times a. Our a here is 2 plus n minus 1 times the difference. Our difference is also 2. Okay? So what does this give us? We get n over 2 into 4. Distribute, we get 2n minus 2. Sn is equal to n over 2 into 4 minus 2. That's just 2. We write it as 2n plus 2. Okay? So simplifying this in our last step, for Sn should be equal to n over 2 times 2n. Our 2's will cancel there. We get n squared. Then on n over 2 times 2, 2's cancel again. We just get n. Okay? So basically here we have a function. This is a function. You can think of it as f of x on this side and some expression with x on this other side. Okay? Let's actually write it out as it is, as x squared plus x, if we just want to think in terms of x. Basically, it is a function. It's the same as the function f of x is equal to x squared plus x. Okay? So, how does this function behave? If we wanted to find the limit as x approaches infinity of f of x, that'd just be equal to the limit as n approaches infinity of s of n, because they are the same function. Okay? So, what does this mean exactly? This is saying, what does Sn approach? As we get an infinite number of terms. Or a bigger and bigger number of terms. And this is just basically the sum to infinity. That is the sum to infinity. It's the value that Sn is approaching as n approaches infinity, or as the number of terms approach infinity. Okay, so let's actually see whether we can evaluate this. The limit as n approaches infinity of s of n. What do you think this will be equal to? Let's try and evaluate this without drawing a graph for it, first of all, because the graph is quite complicated since it's only discrete valued. You probably don't know what that means at this point, but you can look up on it. Discrete valued functions. Discrete valued functions. But you don't need to know about this to understand this concept. So if you're interested, you can just go and look up discrete valued functions, but they aren't necessary for you to understand this. Okay? So the reason why we're not drawing the graph is because it's quite complicated since it's discrete valued, which you haven't covered in your metric syllabus and which you will not cover until varsity. Okay? So we want to find the limit as n approaches infinity of s of n. So without looking at the graph of this function, can we try and evaluate it? What does s of n approach? Let me just change colors here. What does s of n approach? As n goes to infinity, that n goes to infinity. It's the same n. So what does Sn go to as n approaches infinity? We know that since we're squaring here, we're just going to get bigger and bigger squares, right? Since you're squaring a number, like if your input, if the number that you're squaring gets bigger and bigger, your final answer after squaring will be bigger. And basically this is the same as the function x squared, remember? And we know that x squared approaches infinity. Oh, just circle the right thing there. X squared approaches infinity as x approaches infinity. So we know that this part, the first part of Sn, will approach infinity as n approaches infinity. And what does n approach as n approaches infinity? The answer is already in the statement. N is approaching infinity, right? Think about that. So that also approaches infinity. So we just have infinity plus infinity. which is just infinity. It's not 2 times infinity, it's just infinity. When you add two infinities together, you just get another infinity. Okay? Doesn't behave like numbers. So we know that Sn must be approaching infinity. Okay? So you'll realize that for this specific sequence, we can see that Sn is approaching infinity, right? As n gets bigger and bigger. So it's not approaching a specific number. We say that this diverges. The series diverges. Okay? That's an important word. So when we say that it diverges, Sn is not approaching a specific number. Okay? So Sn in this case was approaching infinity, right? And infinity is not a number. It's just a concept that we use to represent something that's very big. So Sn, it's not approaching a specific number, right? That's the definition of divergence. So we can see that this series here, in our example, is divergent. Okay? So as you do more and more examples, you'll realize that all arithmetic series with a difference that is not equal to 0 are divergent. Okay? So let me just write that out. All arithmetic series with a difference not equal to 0 are divergent. That means that they all diverge. Their difference is not equal to 0. Okay? And even if the difference is equal to 0, they can still diverge. So just don't pay much attention to the not equal to 0 part, because it might be a bit confusing. But just keep in mind that all arithmetic series are divergent. As n approaches infinity, they'll all diverge, or all the ones that you usually cover will diverge. There are a few special cases, but we won't go into those. Okay? So just keep in mind that all arithmetic series will diverge as n approaches infinity. So that means that it will be useless for us to calculate the sum to infinity for an arithmetic series. It will be useless for us to try and calculate this because we know that there is no answer for it. It will be infinity or some other funny result. So there's no use in calculating the sum to infinity for an arithmetic series. And if you go actually a bit further, you'll realize that quadratic series are all divergent too. Same as the arithmetic, they're all divergent. So there's no use in calculating the sum to infinity for arithmetic and quadratic series. So the reason why we've gone through this entire explanation is just to solidify that this is the reason why we do not calculate the sum to infinity for arithmetic and quadratic series. Exclamation marks. So don't ever be tempted to calculate the sum to infinity for an arithmetic series or quadratic series. You'll just be wasting your time. Okay? So all of that explanation is just to fully explain why we don't calculate the sum to infinity for those two types of series. Okay, so let's move on now to calculations that we can actually do, which are sum to infinity for geometric series. Okay, so remember what the sum to infinity is in the first place. As we had said, sum to infinity is just what Sn approaches as you get a lot. I'll just write a lot to represent an infinite number, because there's really no such thing as an infinite number, because infinity is not a number in the first place. So it's what Sn approaches as you get a lot of terms to add up. Okay, so if you're just adding up whole bunch of terms that are getting huge, like approaching these huge numbers, that's basically calculating the sum to infinity. Okay, adding up that huge number of terms. All right, so that's what the sum to infinity is, as we had said in our previous examples with the other two types of series, which we will forget from this point onwards. Whenever you think of sum to infinity, forget arithmetic and quadratic series. All right, so sum to infinity for geometric. Okay, so let's look at some examples. We talked about divergence, right? Which basically means that, let me just write it here. Divergence is when the sum to infinity does not exist, right? And we concluded that arithmetic and quadratic series are divergent, so their sum to infinity does not exist. Okay, so we'll also talk about another thing. Just move this down. We'll also talk about convergence, and I think you can guess here that this means that Sn does exist. S infinity, that is, sorry. S infinity, sum to infinity does exist. That's when the series is convergent. So convergence just means that the sum to infinity does exist and it's equal to some number. Okay? So let's look at some examples. We're looking at geometric series now. So consider this series. Say we have 2 plus 4 plus 8 plus 16 plus 32 and so on. Okay, so if we want to think about the sum to infinity for this series, what do we have to actually look at? What is this series approaching as n gets bigger and bigger, as we get more and more terms? If you just think of it this way, let's say that our first term, let's represent that 2 by this tiny block here. If you take this and you add it to the 4, which is an even bigger block, then you add it to the 8, then add it to the 16, add it to the 32, add it to 64, and whatsoever, as you get bigger and bigger blocks, adding up. As you get bigger and bigger blocks, let's say that you wanted to calculate the size of the final object that you get after adding all of these blocks together. This object will obviously be huge since you're adding bigger and bigger blocks to it, right? So we would say that the sum to infinity for something like this does not exist. It's divergent because it's getting bigger and bigger. You can always add another box to make it already larger than it was. Okay, so a series like this is divergent. It's divergent. But before we move on to another example, just notice this. Our r here is 2. Okay? Just keep that in mind. Our r is 2 in this example. Let's move on to our next example. Say that we had a series that looks like this. 3, 1, 1 over 3, 1 over 9, 1 over 27, 1 over 81, and so on. Okay? Let's try and represent this with the blocks, the squares again. So basically, we're starting off with our 3, which is the biggest block here. Then we're adding up smaller and smaller blocks. Let's say that's 1. We're adding up the next block, which is a third. The other block, which is 1/9. The next block, and the next, 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 and the next. Okay, so these blocks are getting smaller and smaller and smaller and smaller because our fractions are getting smaller here, right? 1 over 27, 1 over 81, 1 over the next one. So they're all getting smaller. The terms in this series are getting smaller. So we would expect that if we were to add up all of these terms, we could approximate what all of them will be equal to if we just add an infinite number of them. Because at some point here, all of the other tiny blocks can basically be ignored because their size is close to 0. Okay? Since they're getting so small, we can basically ignore their size and stop counting at some point here and just add up all of the things before and say that's the sum of all of them. Okay? So we're approximating. We can approximate. Okay? So in this case, since we can approximate what the actual value of the sum to infinity is, we would say that the sum to infinity exists. So this series is convergent, right? And the reason we say this, I'll say it again, is because these blocks are getting so small that at some point around here, let's say for example, it doesn't matter. All of these other ones that come after don't matter anymore because they're so tiny. So you can just stop counting here and add up all of these other ones. Then that will be your sum. Okay? So in that case, our series here can be said to be convergent. And let's look at what the value of r here is. Our r here is 1 over 3. Okay? So in our previous one, we had an r that's equal to 2. In this one, we have an r that's equal to 1 over 3. Okay, so there should be a pattern here. What differentiates? Let me just write it out. Or what determines whether a geometric series converges or diverges? What determines this? What makes a certain geometric series converge and another one diverge? So if you think back to the previous video? In our previous video, we looked at something like this, where we had this interval here. We talked about this interval, right? And we said that when our r for a geometric series is in this interval, each term that you calculate gets smaller and smaller, right? So if we think about it, what are the properties of a convergent geometric series? For a convergent geometric series, the terms get smaller, very small, as you go on to the millionth term or something. as we go on to the millionth term, the number there will be extremely tiny. Okay, so the properties, or the main property of a convergent geometric series, is that the terms get smaller. Then what's the property of a divergent geometric series? It's that the terms get bigger, a lot bigger. Okay, so, and when we say bigger, we're not talking about the signs. We're ignoring negatives and positives. We're just looking at the number straight, absolute value. Okay, just if you forgot what absolute value is, just refer to our previous video. Okay, so the terms in a divergent geometric series get bigger and bigger, and the terms in a convergent geometric series get smaller and smaller. Okay, so for them to get smaller and smaller, they need to be in this interval, as we had said before in our previous video. So they need to be in this interval for them to be smaller and smaller. So we can conclude that for them to converge, they need to be in this interval, right? Because we know that for a series to converge, the terms must get smaller and smaller. And for the terms to get smaller and smaller, R must be in this interval here. Okay? So we can say the opposite about divergent geometric series. It's for it to diverge, R must be outside of this interval. Okay? So let's write all of that down. For a divergent geometric series, R is less than -1, or R is greater than 1, right? Or we can simply say that it's outside of this interval here, right? So for a convergent geometric series, R must be in this interval here, as we had said. So let's look at our examples and see whether they actually follow this rule. In our examples here, our R was 1/3, and 1/3 is definitely in this interval. So it should be no surprise that it's convergent. Okay? Then let's look at our other example here. Our R was equal to 2, and R is definitely outside of this interval. So it should be no surprise as well that it's divergent. Okay, so we can see that this rule holds and it's consistent for all geometric series. So for you to be able to test whether a series is divergent or convergent, you need to check whether it's in this interval or outside of this interval. Okay, so that's basically it on convergence and divergence. So the last thing that you need to know is actually how to calculate this. Okay, so we know that for s to infinity to exist, we can conclude now at this point that for the sum to infinity to exist, R must be between -1 and 1. So we're just writing it down mathematically. We're writing our conclusion mathematically. So let's see if, do you think it would be possible for us to come up with the formula for the sum to infinity, for adding up all of this infinite number of terms? And the answer is yes, as long as the series is convergent. Okay, so let's see how we would do that in the first place. So we know that Sn is equal to a over r to the power n minus 1 over r minus 1. Okay, so let's look at this. just change colors again. Our sum to infinity is equal to the limit as n approaches infinity of Sn, as we had written before in our previous explanations when we were covering arithmetic and quadratic divergence. So we know that the sum to infinity is just the limit as n is approaching infinity of Sn, right? What is Sn approaching as n gets bigger and bigger as it approaches infinity, right? So we know what the formula for Sn is, so let's just write that down. It's a over r to the power n minus 1 over r minus 1. Okay, so what we need to keep in mind is that r is in this interval here. Okay, so what we can think of is what does r to the power n approach as n gets bigger and bigger and bigger? What does that approach? It should be approaching 0. Okay, and the reason why we say that is, remember our example where you had 1 over 2 to the power x. As x went to infinity, our expression here, 1 over 2 to the power x, also went, it didn't go to infinity, it went to 0, because our fraction was getting smaller and smaller, right, as x got bigger and bigger. So it's the same here. Remember that r is a fraction because it's between -1 and 1. It's less than 1, so it's a fraction. So as x gets bigger and bigger, our fraction here, our fraction r to the power n, will get smaller and smaller. So r to the power n should approach 0 as n goes to infinity. So this will be equal to a power 0 times 0 minus 1 divided by r minus 1. Okay, I hope you understand that, because I'll say it again. When r is in this interval, remember that for this to actually exist, for the sum to infinity to exist, r must be in this interval, right? Because it must be convergent. So our r will be some fraction like 0.8, 0.5, 0.2. And when I say those are actually decimals, but you could just write them as fractions, right? So there are all those small numbers. So when you raise a small number like that to a bigger and bigger exponent, which is basically what we're doing here, n is going to infinity, right? That's what our limit says. As n goes to infinity, this entire fraction here, r to the power n, will go to 0. Just refer back to our previous example with this, if you're still a bit on the fence about that. Okay, so go back to blue. We have a times 0 minus 1, which is just -1 over r minus 1. Okay, so what we can do is take the negative outside and have a over r minus 1. Then we can take the negative back in and put it in the denominator. This will be equal to -r plus 1, because minus r, then minus and minus is plus 1. Okay, so that, if we just rearrange, we get a over +1 minus r. So that is equal to the sum to infinity. That's the formula for the sum to infinity for a convergent geometric series. Okay, so that's the formula that we come to at the end of the day, and that's the formula that you would use to calculate the sum to infinity for a convergent geometric series. Keep that in mind. R must be in this interval. R must be in this interval for this formula to work. Okay, so that is our formula. And these have been the basic concepts for convergence and divergence, convergence of geometric series, the formula, and the properties. Okay, so it should be simple for you to just apply this formula from now to find the sum to infinity for a convergent geometric series. Convergent meaning that R is in this interval. Okay, so that's the video, and we have come to the end of our series the end of our series, not mathematical series, but series of videos. We've come to the end of our series of videos for this week on sequences and series. The next video will be a short one on a few extra concepts, challenge questions, and so on. So stay tuned for that one, and we hope that you will enjoy the rest of your day if you're still watching this during the day, and we will see you soon. Goodbye.